Hello everyone. Today we are going to analyze this frame using strain energy method. In this frame there are two columns, column AB and column CD, and there is a beam BC. In both of the columns there is no load. In the beam BC we have uniformly distributed load 48 kN per meter. It is acting for the whole span. In the joint B, there is a nodal point load 12 kN. It is acting towards the right side. Height of the column AB is 5 meter. Height of CD is 2 meter. And the length of BC is 4 meter. In the point A, there is a fixed support. And in the point D, there is a roller support. In this frame, the number of unknown reactions and moments are 4. In the point A, we have the horizontal reaction, vertical reaction and movement. And in the point D, only we have vertical reaction. So totally 4. The available equilibrium equations are 3. The degree of static indeterminacy will be 4 minus 3, so that it will be 1. Let us keep VD as the redundant. We know the formula for the strain energy due to bending. We have to make sections. In this frame, there are 3 different parts, AB, BC and CD. So we have to make 3 sections, one in AB, one in BC and one in CD. You can see that I have made 3 sections. This section I have made at a distance of x from B, this section at a distance of x from C, and this section at a distance of x from D. Since there are 3 sections, we have to split this formula into 3 parts. This is for this section. Here the limit is 0 to 2. This is for this section. Here the limit is 0 to 4. And this is for this section. Here the limit is 0 to 5. To find the moments M1, M2 and M3, we are going to use left hand side rule. Clockwise will be negative and anti-clockwise will be positive. Let us find M1. Up to this section we have only VD. For VD there is no perpendicular distance. In this case M1 will be 0. Since M1 is 0, this whole term will become 0. So no need to consider this term. Let us find M2. Up to this section we have VD and uniformly distributed load 48. VD is acting in the anti-clockwise direction, so that it will be positive and the distance is x. So VD into x. The UDL is acting in the clockwise direction, so that it will be negative. We know that with the UDL we have to multiply the distance and then the distance by 2. 48 upon 2 it will be 24. X into x it will be x square. Let us partially differentiate M2 with respect to VD. For VD it will be 1. Here there is no VD. In this case the differentiation will be 0. 1 into x it will be x. Let us find M3. Up to this section we have VD, UDL and the point load 12. VD is acting in the anti-clockwise direction, so that it will be positive and the distance is 4. So for VD, the UDL is acting in the clockwise direction, so that it will be negative. We know that with the UDL we have to multiply the distance and then the distance by 2. This load is acting in the clockwise direction, so that it will be negative and the distance is x. Let us partially differentiate M3 with respect to VD. For VD it will be 1. In these two terms there is no VD, so the differentiation will be 0. 1 into 4 it will be 4. Since in the point D there is a vertical reaction VD, The vertical deflection at D will be 0. When we partially differentiate the strain energy with respect to VD, we will get the vertical deflection at D, which is 0. Let us partially differentiate U with respect to VD. When we partially differentiate this and this with respect to VD, we will get this. We can eliminate 2. 1 upon EI is common. We can take it outside, and on the other side 0 into EI, it will be 0. In this equation, let us apply the moments and the differentiations. When we multiply these two, we will get this, and when we multiply these two, we will get this. After integrating and simplifying, we will get VD. For VD, we will get 96.87 kilonewton. By applying this rule, we can find VA. Then, by applying this rule, we can find HA. To find MA from the point D, let us take a moment about A. BD is acting in the anticlockwise direction, so that it will be positive, and the distance is 4. The UDL is acting in the clockwise direction, so that it will be negative. We know that with the UDL we have to multiply the distance and then the distance by 2. This load is acting in the clockwise direction, so it is also negative, and the distance is 5. Let us assume that MA is a hogging moment, so it will be acting in the anticlockwise direction. In this case, it will be positive. For MA, we will get a positive value. That means our assumption is correct. MA is a hogging moment. We can draw the shear force diagram directly. Otherwise, first we can draw the free body diagram. From that, we can calculate the shear force values. These are the shear force values for the column AB. These are the shear force values for the beam BC. In the column CD, there is no perpendicular load, so there will be no shear force. This is the shear force diagram. In this point, the shear force becomes 0. In the beam BC, in this point, there will be maximum positive bending moment. We can make a section in this point and find the distance. You can see that I have made a section in that point at a distance of x from B. We know that in this point the shear force is 0. Using that we can find x. Let us find the moment at A. At A we have MA, which is acting in the anticlockwise direction, so that it will be negative. Let us find the moment at B. MA is acting in the anticlockwise direction, so that it will be negative. HA is acting in the clockwise direction, so that it will be positive, and the distance is 5. For the moment at B, we have got a positive value. That means it is a sagging moment. Now let us find the maximum positive bending moment in BC. MP is acting in the clockwise direction, so that it will be positive. The vertical reaction is acting in the clockwise direction, so it is also positive, and the distance is 1.98. The UDL is acting in the anticlockwise direction, so that it will be negative. We know that with the UDL we have to multiply the distance and then the distance by 2. Finally, we will get 97.75. Using the left hand side rule, we can find the moments at D and C. Both of them are 0. This is the bending moment diagram. If we draw this diagram in the opposite directions, that is called the bending moment diagram on the tension side. Alternatively, we can draw the bending moment diagram by superposition method. Let us see how to draw this. First, using the loads, we have to draw the free movement diagram. In the columns AP and CED, there are no loads, so there will be no movement. We should not consider the nodal point load, so only one is remaining, the UDL. Using this formula, we will get this value. Then we can draw this diagram. Using the end moments, we can draw the end moment diagram. Then we have to combine both of them so that we will get the bending moment diagram. Now we are going to end this session. Thank you for watching this video.